In this next problem, we're going to go through a hypothesis test. In this problem here, it's going through and referring to the Punnett square testing Gregor Mendel did when doing genetics experiments with plants. We want to go through and test Mendel's claim that the proportion of yellow pea offspring is equal to 25%. He went through and did an experiment with pea plants and found that 497 yielded green peas, while 273 yielded yellow peas. And we want to know if this proportion of peas can be considered equal or close enough to 25 for the population value to be considered 25%. So we want to start by every hypothesis testing problem by stating the null and the alternative hypothesis. And so we have the H naught and the H sub 1. And so we state our null and our alternative hypotheses. And for this problem here, we're testing a claim about proportions. And so that's why I'm using P here. If we were testing a claim about means, I would be using mu here. If we were testing a claim about standard deviation, I would use sigma. If we were testing a claim about variance, I would use sigma squared for this value here. Also in this problem, they tell us the claim is that the proportion of yellow peas is equal to 25%. And so if the claim includes equality, the claim is the null hypothesis. And that's helpful here for wording our conclusion. Now, the null and the alternative hypothesis always have to contradict each other. Our null always includes equality, but our alternate could be a not equal or a greater than or a less than. But in this case here, since this is a not equals, this implies that we have a two-tail test. If it was a greater than or a less than, then we would have a one-tail test. Next, we want to go through and state the critical value or the critical values. In this case, since we have two tails, we have two critical values. We're testing a claim about proportions, which lie on the standard normal distribution, the bell-shaped distribution. That's symmetrical, has a total area of 1 underneath it. We want to figure out what are these two critical values. These critical values separate the rejection region from the non-rejection region. Let's go through and draw the rejection region here based on our alpha of 0.05. We want to go through though and split that up into two parts because we have two tails. And so we're going to have two sections here with an area of 0.025 and 0.025. If we add these back together, we get back to our alpha of 0.05. We next want to go through and determine what the critical values are. We can go through, and there's a few ways to do this. If we want, we can use the z distribution located at the end of the packet here. This z distribution will go through and tell us a z-score value and its area to the left under the distribution. So we want to go through and scan this sea of numbers here, looking for which z-score has an area to its left of 0.025. And when we scan through it, we find right here, we have a 0.0250, so that's exactly the value we're looking for. And we have it at a negative 1.9. Then we go up here to get the 6, so negative 1.96 represents the critical value here. And so we have negative 1.96. And the nice thing about the z distribution is it's symmetrical, and so I know that this must be a positive 1.96 on the right-hand side. And so our two critical values are positive 1.96 and negative 1.96. Next, we want to go through and get the test statistic using our formula here. Z naught equals p hat minus p over the square root of p times 1 minus p over n. So p hat here goes through and represents the sample proportion, while p represents the population proportion. In this case here, we're going to take it from the null. The p equals 0.25. This is the value we're testing for our test statistic to see whether this value is sound. And so we want to figure out what p hat is and n. So going into the problem, we have the 497 and the 273. If we add those together, we see we have a sample of 770. And then to get our p hat, our proportion of yellow peas, we take our 273 yellow peas and divide it by our n, our total number of peas, to get our sample proportion. We then can go through and plug these on into our formula and compute to see what our test statistic is. So in doing so, I'm getting 6.996. Now we want to take this test statistic and plot it on our graph above, our graph we have right here, and see if this test statistic lands in a red critical region. It's important to note here that this distribution extends off infinitely, and so I can extend my axes here, and this line is getting asymptotically closer to the axis over time. We still have a small gap though of this red area, this red rejection area, this rejection region in place here, and our test statistic is landing in the red rejection region, so that implies that we are going to reject the null in this situation. So the problem now is asking, was the null rejected? And interpret the result. So what does this mean to reject the null? Our claim was the null, but we're going through and we're rejecting the null. So it appears that we have enough evidence to reject this claim. One piece of information I find useful for wording the conclusions is this figure here. So at the start, you go through and you read the problem. If the original claim contains the condition of equality, in this case we had yes, then that means our claim is the null. In this case, do you reject the null? Yes, we rejected the null. And so in wording our conclusion, we can say that there is sufficient evidence to warrant the rejection of the original claim. And so we're going to be going through and we can use this to help us word this conclusion. And so the null was rejected. The null contained the condition of equality. And since we're rejecting the null, we can go through and say that we have sufficient evidence to not support but reject the claim. Oopsies, there is significant evidence. Let me fix that here. And so at a confidence level of 95%, there is significant evidence to reject the claim that 25% of the P offspring are yellow. Next, let's go through and see how the confidence interval contains to this result. So based off our hypothesis test here, it appears that Mendel is wrong. So next we want to go through and take a look at a 95% confidence interval for this situation. And so we have our formula here for constructing a confidence interval. It's a little bit different. It looks a little similar, but it is a little bit different than our last formula. We come up with this compound inequality where we have P, the population proportion that we're trying to estimate. We're coming up with a range of values to estimate the population proportion based on P hat, the sample proportion. And so we're able to go through and plug in the same values from before. We have our same critical value because we have a 95% confidence interval. That means we have an alpha of 0.05. And I can go through and plug in all of my values. We just have a plus sign over here. And we end up with this range of values. And generally, we round these to 3 decimal places for proportions. And so it looks like the population proportion of yellow P offspring is between about 32 and 38.8%. And so we can go through and now interpret our confidence interval. And so I'm saying, based on this sample, there is 95% confidence that the population proportion of yellow P offspring is between these two values. Now, there is a chance here, this whole idea of saying 95% confident, there is a chance that we just got a sample that happened to be an anomaly. Maybe Mendel is correct, and we just ended up with an anomaly sample here. And the whole point here of saying 95% confident is that, well, 95% of the time we're going to get a sample that goes through and behaves the way that the null behaves. We need to be careful, though, about the type 1 and the type 2 errors, which can occur with these hypothesis tests. But in this case here, the confidence interval is confirming the same result we got with the hypothesis test. The reason being is that Mendel thought that the population proportion was equal to 0.25, but this confidence interval, at least based on the sample, is saying that 0.25 is not a possible value for the population proportion. And yeah, so the sample suggests that the population proportion is higher than 25%.